Hi everyone, Ulysses here for Ask Our Experts. Pramit Nandy is with us again in this episode to answer yet another FAQ on motor control. So let's see how he can help us this time. Pramit, in the previous video we had a brief overview of the field-oriented control algorithm for BLDC motors. Tell us, how do the different components of the BLDC speed control algorithm work in FOC?
Hi Ulysses, that's a very good question. We have been asked about this question several times, so I'm great that I'm talking about this in the video. So speed control in FOC is basically comprises of three PI loops. First one is the speed control loop, the second one is the torque control loop, and the third one is magnetizing flux control loop. All these PI loops work together in tandem to give the best torque response. So there's a motor has position feedback coming in. Motor also has current feedback. So all the three phases that a BLDC motor is driven through. So they are consuming current through each of these three phases. So you don't have to measure all the three phases in a FOC because technically the summation of all the three phase currents sums up to 0. So if you measure 2 out of the 3, you can always estimate the third one. So this current feedback actually goes into something called as Clark transform. So Clark transform is basically moving that current into a two-axis system, which is seen as from the perspective of the stator of the motor. So now it is converted into two vectors, I alpha and I beta. Now these ones are again with reference to the stator are now transformed into rotating coordinate system instead of regular two-axis system, and this is done by another mathematical operation called Park transform. So it's kind of now moving it into or rotating it into a direction which aligns with the magnetizing flux of the rotor. Now output of that is ID and IQ. So IQ is the current loop and ID is the magnetizing flux loop. Now these are fed back to as errors to each respective PI loops, which spit out or output of those PI controllers are VD and VQ respectively, which are voltage vectors. So VD is for doing the flux control and VQ is for torque. Now let's look at from the position feedback. So in this figure, you would see there are a hall effect sensors coming in. So they are actually feeding this information, the phase angle information back to this loop. Now these voltage, remember the voltage loop, voltage vectors that we talked about. Now based on the angle position, it can determine where to place these voltage vectors in the loop so that it can energize the stator of the motor. So it's a little complicated, I know, but I think as we walk through it will be more and more clear. So after this, VD and VQ, they go through something called as another mathematical operation, inverse Park transform. In this case, they are now transferred back into a two-axis stationary system, V alpha and V beta, which eventually are fed back into SVM and inverse Clark transform to make sure that now they are getting the right, they are interpreting these V alpha and V beta into appropriate PWM signals, which are then given back to the inverter of the motor to drive or energize the stator. So this is how whole loop works for this control algorithm. But we also throw in the speed control loop into the mix because the speed reference is also coming here from this side. So whenever there is a change in speed, the whole loop adjusts itself to make sure it is giving the right response to the stator to get the desired torque and desired speed. So this is how all the components in a FOC algorithm work.
Thank you, Pramit, for walking us through the various components of the BLDC motor speed control algorithm. To our viewers, make sure to check out our application note AN4064, linked in the description for more info on this topic. And don't forget to subscribe to our YouTube channel to be the first to know when we have more insights from our experts. See you next time.